All right, this is the intro video for AP Calculus AB, section 3.3. And in this video, we're going to be looking at functions that are increasing and decreasing, as well as an intro into the first derivative test. We'll be skipping around the notes just a little bit, so be watching out for that. So we got the blue box here again with the theorem 3.5. You feel free to read that, connect that with what we're going to talk about here. Just a second, we're gonna move down the page just a little bit and maybe try to talk about it a little less math type terms here, but I want you to remember this for sure. Please remember that as we talk about increasing and decreasing, we're always going to be judging this as we move from left to right. As x moves from left to right is the function that we're concerned with. Is it increasing or decreasing? We want to always go in that direction. So let's go ahead and move on down to the bottom of the page and look at what this means now. Okay, so we're going to try to connect this graph with these statements down below. The first statement right here, statement number 1, says if f is continuous and differentiable, then if f prime is greater than 0, so of course that's positive, but let's talk about f prime. Let's remember what f prime stands for. F prime stands for the slope of f. So hopefully that makes sense when you think about it. It's saying if the slope of f is positive for all the x in the interval a to b, then f is increasing. So if the slope of f is positive, then f is increasing. And so we're going to say that by saying this statement right here, if f prime is positive. Let's not refer to the slope of f, although that's certainly a good statement. Let's refer to f prime being positive, knowing that that means we're referring to the slope of f. If f prime is positive, then f is increasing. And like I said, that's because the slope of f also would be positive there. Statement number 2, if f is continuous and differentiable, and if f prime is negative. So again, let's remember that f prime is just the slope of f. So if the slope of f is negative, then f would have to be decreasing on that particular interval. And the statement number 3, if f prime is 0 for all the x in AB, then f would be constant. So again, f prime is referring to the slope of f, and so if f prime is 0, then f would have to be constant. So if we look up here at our graph and try to make this connection here on this interval on the right, you can see that from here over to the end, f is increasing. And if you think about any point that we looked at in there, any point that we looked at, you would see that f prime is positive because the slope of f is positive. Over here on the left, again on this interval, and since the slope of f is negative, f prime would also be negative on that interval, making it a decreasing function. And of course, the space right here in the middle, you can see that we have a constant, and that would be a place where f prime equals 0. Again, the takeaway here, if f prime is positive, f is increasing. If f prime is negative, f is decreasing. If f prime is 0, then f is constant. And that's all tied together by the fact that f prime is describing the slope of f. Okay, we're jumping ahead a little bit here now. This is a couple pages later in your notes. We'll be doing the examples in between here in class, but we're going to be looking at a very important concept called the first derivative test. And so we've got a few blanks to fill in here, and then we'll look at it. First statement here says relative maxima and minima occur at critical numbers. Of course, that's something we've been studying for a while. And let's keep going here. Relative maxima and minima occur at critical numbers, and critical numbers are places or locations where the derivative of whatever it is, maybe f prime or g prime or whatever we're looking at, is 0 or does not exist. So when we're talking about relative extrema, we're only concerned with critical numbers. There won't be any endpoints to deal with like we have in the past. So the first derivative test is a key feature, a key concept here. So we're gonna look at it. There are three pieces to this, 3 cases, and so we're going to look at each one of these one by one. So the requirements are right here. Let C be a critical number of a function that is continuous on whatever area we're concerned about containing C. F must be differentiable except maybe at C. Let's take a look at the first case. So here it is. If f prime changes from positive to negative at C, then f has a relative maximum at that critical number. If f prime is positive to the left and then negative to the right, then we have a relative maximum. Let's take a look at how that works. So we're going to look at a couple of graphs here. The graph on the left is a graph of f, and the graph on the right is a graph of f prime. So on the graph of f, let's look at that first. So I would say right here, I've got a relative max, right? So relatively high point. There you go. Now let's focus on the area over here to the left, from here to there. If you think about any point on that particular interval there, f prime would be positive, wouldn't it? F prime is positive. And then if you look at the interval to the right, say from here over to here, any point on that particular interval, f prime is going to be negative. So you can see that to the left f prime is positive, to the right f prime is negative, therefore we've got a relative maximum. So if f prime goes from a positive value to a negative value, then f has a relative maximum. Let's take a look at the graph of f prime. This is another way to look at it. So once again, roughly at -3, we've got something going on. Right here, I would say that since this is a graph of f prime is equal to 0, right? It's going through the x-axis. So we get a value of 0 there. To the left, you can see that f prime is above the x-axis, and so we'd say that f prime is positive. And let me clean that up just a little bit here. F prime is positive. And then over here to the right, you can see that f prime is now dropped below the x-axis, and so f prime is now negative. So again, whether you're looking at a graph of f or a graph of f prime, we're still looking for where is f prime going from positive to negative. If we can find that place, we have a relative maximum. So take a minute and kind of think that one over. The next two cases should kind of follow logically from that case. All right, case number 2. Similar to case 1, it says if f prime changes from negative to positive, so it's the other way around now, then f has a relative minimum. If f prime goes from positive to negative, then f has a relative minimum. Let's take a look at the graph of f. I would say it's pretty clear that we have a relative minimum right there at x equals 2. So if we carefully look at the interval to the left, we can see there that f is decreasing. Looks pretty clear that f prime is negative over there. And then if we look at the other interval, on the right there from about 2 to 4, we can see right there that f prime would be positive. So we can see f prime going from negative to positive, therefore we've got that relative minimum. Now over here on the right, we're looking now at a graph of f prime, could be illustrated this way as well. Right here at x equals 2, I've got a place where f prime is equal to 0, making that x equals 2 a critical number. Again, we can see that f prime is below the x-axis, that means f prime is negative. And over here we can see that f prime is above the x-axis, meaning that f prime is positive. Since f prime went from negative to positive, then f must have a relative minimum at that critical number. Finally, case number 3, if f prime does not change signs at that critical number. So before f prime was going from either positive to negative, which meant relative max, or f prime was going from negative to positive, which meant relative min. At this time, we're looking at maybe a situation where f prime doesn't even change signs. What that means then is that f of c is neither a relative minimum or a maximum, and technically that makes it what we will later on call an inflection point. So let's take a look here, these two graphs. Graph of f, you can see right about here at 1, we have a place where it looks like you have a horizontal tangent line, right? The graph flattens out, at least for a brief moment there. But on the left, f prime is positive. And on the right, f prime is positive. So f prime doesn't change signs, it stays positive. So that means we have neither a relative minimum nor a maximum. If we look at a graph of f prime, we can see the same kind of thing happening. I've got f prime equaling 0 right there at 1, like we saw before. But to the left, you can see that f prime is above the x-axis, therefore f prime is positive. To the right, you can see that f prime is still above the x-axis, meaning that it's still positive. And so that means that f prime did not change signs. Therefore, we have neither a relative minimum nor maximum. And then the other case here, very similar, of course. We're looking at a graph of f. So right about there, as before, x equals -2. We've got a place where it looks like maybe the graph of f does flatten out just a little bit, perhaps a horizontal tangent line. But to the left, f is going downhill, so f prime must be negative. Over here on the right, f prime is still decreasing, still going downhill, so f prime must still be negative. You can see f prime did not change signs. Therefore, f does not have a minimum or a maximum. Technically, it has that inflection point. Same idea over here. We're trying to illustrate the same thing using f prime. So here is a critical number right there at x equals -2. That would be where f prime is 0. But on the left, you can see that f prime is below the x-axis, meaning that f prime is negative. Over here on the right, f prime is negative because f prime is still below the x-axis. You can see whether we look at a graph of f or a graph of f prime, we can still see here that since f prime doesn't change signs, we'll have neither a minimum nor a maximum. Okay, so those three cases, definitely important, something we'll work with a lot for the rest of the year. We'll be working examples in class. See you then.